If you spend any time on car forums, you've definitely seen the debate. Does horsepower sell cars, while torque wins races? To settle this, let's fire up a desktop drag simulation. We're going to put two identical cars on a quarter-mile track. One makes 1,000 horsepower and 500 pound-feet of torque. The other makes 500 horsepower, but packs 1,000 pound-feet of torque. Before the light even turns green, there is a massive problem with our 1,000 horsepower car. If peak power happens at a standard 5,000 RPM, this specific engine is physically impossible. This formula shows why. Horsepower is calculated by multiplying torque in pound-feet by RPM, and then dividing by a constant, 5,252. The variables are permanently locked together. You simply cannot calculate horsepower without knowing the torque. Judging an engine by horsepower alone is like measuring a distance without picking a starting point. We can make the math a lot easier to visualize if we step out of the garage and into a boxing ring. Think of torque as the physical force behind a single punch. RPM is the total number of punches you throw in a minute. Horsepower is the total damage dealt. If you have a very weak punch, low torque, you'd have to throw tens of thousands of punches to equal 1,000 horsepower worth of damage. This chart tracks their progress in our first simulation. Using a direct 1-to-1 drive gear with no transmission, the high-torque car crosses the finish line in 13.6 seconds. The 1,000 horsepower car's velocity flatlines near the start, taking an agonizing 19.4 seconds. Even with 4 digits of horsepower on the spec sheet, the engine is completely useless if it lacks the raw twisting force required to actually get the wheels moving. To see why our high-horsepower car stalled out, we need to look at the raw physics of rotational force. Think about a rusty nut, or even a heavy wooden door. If you try to open a door by pushing right next to the hinge, you have to push incredibly hard. But if you push at the outer edge near the handle, it swings open with almost no effort. By looking at this top-down view of a wrench turning a nut, we can see exactly what torque is. It is the vector product of your applied physical force and the distance of that force from the rotational axis, or pivot point. If you apply 90 newtons of force to a 30-centimeter wrench, you get 27 newton-meters of torque. But if you extend that handle to 60 centimeters and apply the exact same physical effort, your torque output immediately doubles to 54. Raw physical force isn't the only thing that matters. Increasing your distance from the pivot point is just as critical to making something spin. Engines apply this exact same mechanical advantage to a vehicle's wheels. You can think of gears as continuous rotating wrenches. If you connect a small engine gear to a wheel gear that is twice its size, the wheel will only complete half a rotation for every full rotation of the engine. You cut the rotational speed in half, but you double the torque output at the wheel. Imagine you are riding a motorcycle up a steep hill while carrying a heavy passenger. If you hit that incline in top gear, the engine will likely bog down and stall. When you shift the motorcycle down into a lower gear, you are essentially grabbing a longer wrench. You sacrifice top speed, but you generate the pure twisting force required to beat gravity and pull that weight up the hill. Engine power is a constant, so manipulating these gear ratios is the primary way machines overcome physical resistance. Let's take that concept straight back to our drag strip simulation. This time, we're outfitting both cars with a 4-speed manual transmission and proper gear ratios. With gears multiplying its force, our torque-heavy car suddenly has a massive problem. It produces too much raw force for its tires, instantly breaking traction and just spinning its wheels in place. This graph tracks the horsepower car. The transmission gears multiply its exceptionally low torque, allowing the engine to actually reach its massive RPM ceiling. Through 4 rapid shifts, the velocity climbs sharply, and it wins the race in 9.7 seconds. By using a transmission to multiply force and manage tire traction, total horsepower becomes the ultimate determining factor for maximum speed. We have one final variable to add to the simulation. We are loading both vehicles with 6,000 pounds of heavy bricks. When we rerun the weighted race, the results flip again. The torque-biased car decisively beats the horsepower car. Pulling a heavy load from a dead stop requires pure, unadulterated rotational force. Without it, the engine simply can't overcome the massive inertia. Engineers know this perfectly well. Massive machines prioritize extreme torque and low speeds over horsepower because their primary job is pulling heavy implements through dense dirt, not setting track records. High horsepower dictates how fast a specific amount of work gets done, but high torque dictates whether that heavy work can be started in the first place. Treating horsepower and torque as opposing forces is a basic misunderstanding of physics. They are inherently connected parts of the exact same equation. Torque tells you the raw physical twist the engine applies in a single millisecond, and horsepower gives you the overall mechanical capability sustained over time. Before you argue over engine spec sheets, check the RPM, analyze the gear ratios, and know exactly what kind of physical damage the machine was actually designed to do.